Swayam Prabha. Digital India. Educated India.
So, good morning. So, today we will complete the derivation of the RANS equations that we started yesterday. So, I asked you to work the energy equation, derivation of the RANS energy equation. I hope you have tried to do that. Anyway, let us just once attempt it here and then summarize the equations together. So, when we look at the energy equation, so which is nothing but u dt by dx plus v dt by dy. So, these are the two dimensional steady state incompressible energy equation, alpha into t by dx square plus t square ty dy square, right. So, now when we do the Reynolds decomposition, substitute for u and t. So, we have seen that the Reynolds decomposition for u, instantaneous velocity will give u bar plus u prime, v is equal to v bar plus v prime. Similarly, the instantaneous temperature. So, therefore, if you put a thermocouple, the same flat plate you can consider that we discussed yesterday. Now you heat the bottom wall and you insert a thermocouple somewhere within the thermal boundary layer. Similar to the velocity fluctuations I have drawn, you will get temperature fluctuations. Okay. Therefore, if you apply the proper filter, you should be able to average the instantaneous temperature using this filter and decompose the instantaneous temperature into a mean and a fluctuating parameter. Okay. So, now you can substitute for all of these variables and then average the entire equation, Reynolds averaging. Okay. So, what we are doing here is time averaging. So, for the 2D incompressible steady state, does not matter whether we do a time or ensemble average. So, it will still be the same. So, on the right hand side you have alpha d square by dx square the right hand side is easy. We can apply the averaging rule and separate this into t bar plus t prime bar. So, t prime bar is 0. Okay. So, the mean of the fluctuating quantity is 0. So, therefore, this can be simply written as now once again looking at the left hand side, we have 4 terms here, we have 4 terms here, and again when you split this the way we did it for the momentum equation. Okay. So, for example, this can be written as therefore u prime du prime by dt prime by dx. Okay. So, this we have averaged plus you have u prime dt u bar dt prime by dx average of this plus you have u prime dt bar by dx the average of this plus you have u prime dt prime by dx average. So, out of this if you apply the averaging rule, so this will be 0 and this will be 0. Okay. So, essentially from this you are left with only u prime dt prime by dx average, okay, and this is nothing but by averaging rule u bar dt bar by dx. Similarly, from the second term on the LHS, we have v bar dt bar by dy plus v prime dt prime by dy average. Okay. The right hand side is as it is. So, now we can write this as d by dx of u prime t prime minus t prime into du prime by dx. So, therefore, if you take t prime constant, we will have du prime by dx plus dv prime by dy, which will be 0, okay, satisfying the continuity for the fluctuating component. So, essentially you will have therefore v bar dt bar by dy. On the left hand side you will have d by dx of u prime t prime bar, okay, plus you have d by dy of v prime t prime bar is equal to RHS. Is it okay? Clear? Right. So, let us now therefore summarize the entire set of RANS equations, momentum and the energy together. So, when I am going to write it, I am going to take this term, the fluctuating term, I am going to use that towards, put it towards the right hand side. Okay. So, I will keep the conventional advection term on the left and take all the new quantities arising out of the turbulent fluctuations towards the right hand side. So, we will see why we are doing it. Okay. So, for example, now therefore, the final set of RANS equations. So, the continuity for the mean velocity is satisfied, and so is for the fluctuating component, and then anyway we are not going to now solve for the fluctuating component. Okay. We will only construct the equations for the mean component. This is what we are going to solve. We will see how we account for the fluctuating component quickly, and then the x momentum equation will be u bar du bar by dx plus v bar du bar by dy. So, I am going to take the turbulent stresses towards the right. I have minus 1 by rho dp bar by dx plus, now I have nu into d square. Let me first write this and then I will combine it. Now, I have additional terms minus, what do I have? Minus dou by dou x of u prime, this is in the x momentum equation, u prime bar, right, and minus d by dy u prime v prime bar. Is it okay? I am just taking this to the RHS. Now, if you observe the way that we have written this, okay, we can also write this. Let me multiply throughout by rho first. Let me keep the rho here. So, this is dynamic viscosity, and therefore, I can take rho inside because this is incompressible, does not matter. this term, the diffusion term, viscous diffusion, and now the turbulent diffusion. So, the turbulent diffusion is although arising from the inertial term, I have taken it to the right. Now, I am going to combine it with the viscous diffusion here. Okay, so, therefore, I can write this bunch of terms as d by dx common, and this is nothing but mu du by dx minus rho into u prime bar. So, this is one set of terms, plus I have similarly d by dy of mu du by dy minus rho into u prime v prime. So, I am intentionally writing it in this way because I want to combine the turbulent stresses with the viscous stresses, and I want to group them together. So, that we will now draw an analogy. Okay. So, similarly the V momentum equation. So, rho into we have u prime u bar dv bar by dx plus v bar dv bar by dy. On the right hand side we have dp bar by dy plus again I am going to have d by dx mu into what do I have dv by dx minus rho into u prime v prime bar. Okay, I am continuing this plus, so I am just continuing that. So, plus d by dy of mu dv by dy, and I have again minus rho into v prime bar. Okay. So, this will be the structure of my y momentum, and finally the energy equation also I am going to write it in the same way. So, what I am going to do, this alpha is k by rho Cp. So, I am going to multiply throughout by rho Cp. So, I have rho Cp into u bar dt bar by dx plus v bar dt bar by dy. Okay. And on the right hand side I have now d by dx of what k dt by dx and minus correct rho Cp into u prime t prime bar plus I have d by dy of k dt by dy minus rho Cp v prime t prime bar. Is it clear? Okay, I am just rearranging, combining basically the turbulent diffusion with your molecular diffusion terms. Huh?
Mu dou u by dou x should be u bar.
Yeah, all these are mean quantities. You are absolutely right. All these are mean quantities here also. Okay. So, now why I am doing this is I am going to close this problem. Okay, now we have a particular problem in this RANS models which are called as closure problem. So, what it means is now when you did the Reynolds decomposition and averaged it, you have created a turbulent stress which is like u prime, v prime, u prime, u prime, so on and so forth. Similarly, in the energy equation. Okay. So, now you have your molecular diffusion which is giving all this tau xx, tau xy, tau xz, so on and so forth. You have your tau yx, tau yy, tau yz, tau zx, tau zy, tau z. So, apart from that, now you have therefore set of 9 stresses coming from the turbulent inertial terms. So, we can therefore group them as what? Minus rho u prime u prime. Can you fill in all these elements? Minus rho u prime v prime. So, if you write it in a 3-dimensional form, so if you derive this for the xyz momentum equations, then you have minus rho into u prime w prime. So, like that you have all the terms. We have v prime u prime minus rho v prime minus rho v prime w prime, so w prime u prime, w prime w prime. So, apart from your viscous stresses here arising due to the molecular diffusion, you are now adding your turbulent stresses. Okay. So, when you do this, you can therefore draw an analogy to molecular. We name this as turbulent diffusion. Okay. Although this is not a classical diffusion term like molecular diffusion, this is coming from the inertial term, but we, for the sake of convenience, we would like to combine this with your molecular diffusion and name this as turbulent diffusion. Okay. So, in doing so, what we do is we want to avoid the closure problem, because now you have this term. In order to solve for these equations, you need to solve for, therefore, u prime, v prime, u prime, u prime, all the 9 stresses have to be solved, then only we can solve these equations. But you do not have any equation for the stresses, you do not have any governing equation. So, then what can we do? We can construct a governing equations for the stresses by multiplying again the momentum equation with the fluctuating component, for example. Okay. So, like this we can construct another governing equation for the turbulent stresses, but they will have another term with a higher order moments. You will end up with rho u prime v prime u prime, rho v prime u prime v prime v prime. So, all higher order moments will come. So, like this it will keep on going cascading. Now, if you construct again another governing equation for the higher order moments, you will end up with one higher order moment. Okay. So, therefore, this will be a never ending problem. This is called the closure problem. So, in order to close this, here we can actually do it at this level itself. We can close it at any level. You can also construct a higher order equation and then close the higher order moment, but that is not going to be practically useful. So, we will just try to close it here, and how are we going to do that? By doing what is called as a Boussinesq hypothesis. Now, this Boussinesq hypothesis is not the same as what you did in natural convection, this is a different one. So, here Boussinesq, what he says intuitively is that the nature of these turbulent stresses or turbulent diffusion can be modeled analogous to the molecular diffusion, only that we will replace the molecular viscosity with what is called as turbulent viscosity. Okay. So, for example, in this particular equation we can simply say minus rho u prime v prime bar is equal to mu t into du bar by dy, just analogous to the molecular diffusion, but I am going to replace my dynamic viscosity, molecular viscosity, with what is called as the turbulent viscosity. Correct. So, in doing so, now I have closed the problem. Okay. So, I can now solve this equation using this analogy, but still what is unknown is the turbulent viscosity, and turbulent viscosity mu t is not a property, it is not a thermophysical property like laminar viscosity. So, again you have to, it depends on the flow just like your heat transfer coefficient. So, for a given flow problem you have to actually understand how mu t has to be computed. So, for that we then solve additional equations and calculate the turbulent viscosity. So, like this we can evoke the business hypothesis for all the remaining stresses, and therefore, we can combine the laminar diffusion with the turbulent diffusion. So, therefore, for example, in this case how do we replace this using the business hypothesis? Mu plus mu t into du by dx. See how simple it is now, okay, except that mu t is unknown. So, similarly here also this is mu plus mu t times du bar by dy.
Mu t is a constant for all the components.
No, mu t will be a function of position, it will not be a constant.
So, I am saying like dou by dou x.
Yeah, so that we are assuming that this is constant right now. Okay, so we are not using different mu t for the x momentum, y momentum, each derivative. Okay, so because already this is an ad hoc hypothesis which is reasonably good enough. So, there is no point in complicating it. So, let us make it simple and see if it works, and most of the time with reasonable approximation it works. Okay. So, same way you can also use this as mu plus mu t into this is dV by dx. So, similarly when you look at the stresses, the turbulent thermal stresses, we have combined that with the molecular diffusion due to thermal conductivity. Okay, so, therefore, similar hypothesis can also be evoked. So, what we can say is minus rho Cp into therefore u prime T prime can be written as what? Some turbulent thermal conductivity, okay, times dt bar by dx. Okay. So, we can actually therefore combine this as what? K plus kt into dt bar by dx, and this will be k plus kt into dt bar by dy. So, by this manner we have completely closed the RANS equations, we have avoided the closure problem. So, next therefore, when you now calculate the total stress, we have to therefore include the turbulent stress along with the molecular stresses. Similarly, with the heat flux. So, therefore, when we write tau, for example, when we say tau xx, as I said, we are now combining this plus this. This is nothing but mu du by dy, we are combining with your turbulent stresses. So, for example, tau xx will be mu into du by dx minus rho u prime bar. Understand? So, this is the way we calculate the total stress. The total stress has the molecular or laminar diffusion and the turbulent diffusion. Similarly, for the heat flux. So, when we say heat flux in the x direction, how do we calculate now? This is k into minus k dt by dx, right. minus k dt by dx, then plus we have rho Cp u prime p prime bar. Understand? So, when we say stress in the RANS equations, we include a combined action of the laminar and turbulent stresses and the combined action of the laminar and turbulent thermal diffusion together. Now, in fact, if you look at the turbulent, highly turbulent flows, and when we replace this with the Boussinesq hypothesis, so many a times the turbulent diffusion will be at least an order of magnitude higher than the laminar diffusion. Okay? So, in the turbulent region, therefore, most of the time your mu t by mu will be much greater than 1, and so is k t by k. So, most of the times they will be governed by only the turbulent diffusion. The molecular diffusion will have little role to play in the turbulent region. That is why it is very important to account them. We cannot definitely neglect them under any circumstance. So, just like your laminar Prandtl number, now we can define what is called as a turbulent Prandtl number. Since we have now a turbulent thermal conductivity, turbulent viscosity, we can now define a turbulent Prandtl number. Okay, that is your mu t Cp by kT, or this is the ratio of your turbulent momentum diffusivity by turbulent thermal diffusivity. Understand? Okay. So, this is your definition of turbulent Prandtl number. Okay. So, I hope this part is clear. So, now what needs to be really computed is the value of a turbulent diffusion. Okay. And in order to do that, either the turbulent viscosity. So, once you calculate the turbulent viscosity, we can actually fix the turbulent Prandtl number and therefore obtain your turbulent thermal diffusivity. Okay, we do not solve for turbulent thermal diffusivity separately. So, usually we only solve for the turbulent viscosity, then fix the turbulent Prandtl number, usually around 0.9 or something like that, and get alpha t. So, now how do we solve for mu t? So, there are different approaches to that. So, what we call as turbulence modeling. So, I will not spend too much time because I am sure many of you must be already knowing how do we do this, but just I will summarize it. So, we start from the simplest model, which is called the zero equation model or the mixing length model. The mixing length model was originally conceived by Prandtl himself. Okay. This is one of the simplest models. So, what he suggested was to assume that the turbulent viscosity is a function of some length scale and velocity scale. So, and when you look at the effect of turbulent scale, so you have these large eddies which actually transfer energy to the smaller eddies through what we call as cascading. Okay. So, there is a certain length till which the large eddies maintain their size, after which they break down into smaller eddies. Okay. So, this length is called the mixing length. So, Prandtl came out with some kind of a intuitive hypothesis which says that this turbulent viscosity should be a function of the mixing length and some velocity scale. Okay. So, he represents the velocity scale to be a function of mixing length times the derivative of the mean velocity. For example, if this is your y, okay, and you have a certain mixing length Lm, the corresponding velocity scale of turbulence is given by Lm into du prime by du bar by dy. Okay. This is some scaling and some hypothesis. So, therefore, he relates this turbulent viscosity by multiplying another length scale to this. So, this is your length scale and this is your velocity scale. Okay. So, what is this mixing length? So, the mixing length, if it is in a purely turbulent regime, it is some constant.
Sir, can you say what do you mean by mixing length?
So, mixing length actually is some kind of virtual or theoretical length. If you have a eddy of a given size, so it will actually break down into a smaller eddy after it travels down because of the action of the wall. Okay. Finally, it has to be dissipated as heat. Okay. So, there is a certain length till which it does not break down, it retains its original size. So, that is called the mixing length. Okay. You cannot of course measure all this, okay, unless it is the large eddy. For all the eddies you cannot find what is the mixing length. The mixing length of course will be different, but then he did not account for all of this. So, all he says is that we can relate the turbulent viscosity to a mixing length scale and a velocity scale. And how do we calculate the mixing length? So, now that we have closed it. So, in the zero equation model we have closed the turbulent viscosity to be a function of the mean velocity. The only unknown is the mixing length. So, he is giving an empirical correlation for mixing length should be some constant times y. What is this constant? This is called the von Karman constant. Which is equal to 0.41. Now, due to the presence of the wall, if it is purely turbulent, the mixing length will be just a constant times y, but due to the effect of wall, this mixing length actually varies. So, as you go closer to the wall, this mixing length will become smaller and smaller. You can imagine that the effect of wall gets very strong. So, the mixing length has to reduce, it has to break down faster and faster. So, therefore, to account for, there is a damping function which is multiplied to this, and he proposed a damping function like something like this. So, this is your damping function. So, what is y plus? So, y plus is a non-dimensional position which is y times what we called as friction velocity divided by nu, and this friction velocity is nothing but square root of wall shear stress by rho, and this constant A is nothing but 26. So, you understand that conceptually Prandtl had proposed this mixing length theory in order to simply close the turbulent viscosity without having to solve additional equations, right. So, this works fairly well if you have a flow which is attached to the wall, okay. So, like a classical boundary layer theory, but what happens when there is a detachment, flow separation? So, in that case then the mixing length model fails because there is no boundary layer, okay. You cannot locate the sublayer and so on, okay. So, all this will fail. So, therefore, then for separated flows or flows with pressure gradients, this kind of simple approach will not work, okay. So, then in that case you have to go for more advanced models which will now involve solving additional equations. So, these are your classical turbulence modeling equations. We will just quickly list them. So, you have what is called as a one equation model, which is slightly more complex than the mixing length model. So, in this case you solve for one additional equation for the turbulent viscosity. So, you construct one additional equation for turbulent viscosity and solve for mu t. So, this will be additional partial differential equation along with your momentum and energy equations. Okay. Now, for more complex flows, recirculating flows, flows with strong curvatures, pressure gradient, rotation and so on, then we start going for 2 equation models. So, they involve solving additional equations, one for the turbulent kinetic energy and turbulent dissipation rate. Epsilon. So, this is denoted by K. So, we call this as K epsilon models, for example. So, there are several bunch of these 2 equation models. We have K epsilon, we have K omega, combination of these 2 which is called the shear stress transport model. This is called actually some kind of vorticity constructed out of the epsilon equation and modified. So, so you have several kinds of approaches in 2 equation models, okay. And then you can also solve, rather than applying a closure, the business hypothesis, we can construct equations for the turbulent stresses, okay. That is u prime, we can have a partial differential equation u prime v prime, and then therefore we can solve for totally how many stresses. So, we have 9, out of that 3 are symmetric, okay. So, we have 6 stresses plus 1 additional equation for dissipation rate, okay. So, therefore, we call this as Reynolds stress model. So, these turbulent stresses are also called Reynolds stresses. So, we can solve PDEs for u prime, v prime, so on, okay. But anyway, there has to be a closure for the higher moment, which will be u prime, v prime. So, that will be closed in a different way, right. So, therefore, in 3 dimensions we solve for 6 stresses plus 1 equation for dissipation rate. And then without doing any of the Reynolds averaging, we can actually do what is called, we can directly resolve all the dominant structures, eddies, by using a direct resolution by solving the Navier-Stokes as it is, but we use a spatial filtering, which is the grid size, to filter out the eddies which are smaller than the grid size. So, those will be modeled, okay. The eddies which are larger than the grid size will be resolved. So, this is done in the large eddy simulation. And finally, if you can resolve all the length and time scales without any filters, okay, and without any turbulence model, we call this as direct numerical simulation. So, these are the increasing complexity of the turbulence models, okay. So, most of the industrial problems are satisfied by stopping here, okay. So, some of the research problems, they want to go deeper, they probe into LES and DNS, but finally for practical purposes you do not need all these data. So, although you are solving for the fluctuations and so on, what are you going to do with that, okay. So, we do not have much ways of interpreting all the fluctuating components. It may be looking good for understanding how they interact and so on, but finally for practical engineering purposes, working with fluctuations, u prime, t prime does not have any meaning. Therefore, we are more or less happy with stopping with the 2 equation models. So, all these 2 equation models give you is the mean components, that is the mean velocity, mean temperature in turbulent flow field, okay. So, once you understand the mean, once you can predict the mean properties well, they are enough to solve practical problems. For example, when you now define heat transfer coefficient, it will be the gradient of the mean temperature, okay. If you know the gradient of fluctuation, what are you going to do with it? You know there is a fluctuation to the mean, but that is not going to serve any purpose. Okay. So, as long as you can construct a engineering approach to solving turbulence, I think that is a more sustained practical approach. So, although we have techniques using LES and DNS, I do not think these are still in the industry well absorbed. So, they are mostly in the academic exercises, right. So, most of the practical engineering problems have been designed with maximum with the 2 equation models, right. So, I think now hopefully you have some kind of an understanding about the models that are used. Now, what we will quickly do in the remaining 5 minutes, we will try to derive certain relationship between the velocity scale and the position as we go across different layers in turbulence. Okay. So, very quickly we will do that and stop. So, as I already pointed out, when you for example talk about turbulent flow past a flat plate, you have a turbulent boundary layer, right, and there is a viscous sublayer which is close to the wall. So, when you talk about the laminar Prandtl number for example, okay, so that is going to govern only the growth of this viscous sublayer, whereas the turbulent Prandtl number is the one that will govern the growth of the actual boundary layer. And since your turbulent diffusion is much higher than the laminar diffusion, okay, so this will be the dominating pattern and the laminar sublayer will be confined only close to the wall, right. So, now as you go from the wall upwards vertically, so you will be passing through initially the laminar sublayer till a certain height and then into the turbulent region. So, this is your fully turbulent region here, and this is the region where it is only laminar. Because of the effect of wall, there is no turbulent effect seen there. So, now what we can do is derive a relationship between the velocity profile and the local coordinate. So, let us start with the business hypothesis, which says that we can model the turbulent stresses with the analogy of the molecular viscosity. So, we can just write this as mu plus mu t into du prime by dy. Okay. So, if you, what I would like you to do is write this in terms of what we call as a non-dimensional velocity u superscript plus. Okay. So, this is nothing but u by u tau, and u tau is nothing but the frictional velocity square root of tau wall by rho. Okay. And write this in terms of non-dimensional y coordinate y plus, which is y into u tau by kinematic viscosity. So, use this relation, generic one, and express this in terms of u plus and y plus. See, at the wall this will be equal to the wall shear stress tau wall. So, one thing what we can do is multiply and divide by u tau, right. So, therefore, d of u bar by u tau is nothing but u plus. Okay. So, we have du plus, and similarly we can combine the tau wall to this side. Okay. So, you should be able to write this also in terms of y plus. You tell me then what will be the multiplying factor. I will also give you the left hand side, it should come out to be 1. So, what do you get? You will have 1 plus kinematic turbulent kinematic viscosity by laminar kinematic viscosity. Okay. So, now, so this is your equation coming out of the definition of the stress. So, depending on the regime, now let us first consider the viscous sublayer. Inside the laminar sublayer, your laminar viscosity is much more dominant than the turbulent viscosity. So, what will happen to this term? 1 plus nu t by nu. So, suppose let us take viscous sublayer. Viscous sublayer, your mu is much greater than mu t, right. So, therefore, what will happen to this entire term? 1. Okay. Therefore, this will reduce to 1. So, if you integrate this, okay. So, this is your profile of velocity within the viscous sublayer. Now, what happens in the fully turbulent layer? So, in the fully turbulent layer, your turbulent diffusivity is much greater than nu, right. So, then what happens to 1 plus nu t by nu? Will be nu t by nu into du plus by dy plus will be equal to 1. Okay. So, now you can substitute for mu t from the mixing length model. Okay. So, anyway, since mu t is here, you have to close it.
So the tau wall we are using, we are equaling it to u tau square into rho.
U
And then
tau,
only you will get the
u tau square,
into rho.
yeah, correct, correct.
But in the fully turbulent region, how can we use that? How can we use tau equal to tau wall?
See, if you just erase this, the same wall shear stress will be felt, but only you are considering only the turbulent boundary layer, not the laminar sublayer. So, you can call this, in one sense you have a 1 layer model, the other is a 2 layer model. Okay. So, in a 1 layer model, you are considering only the fully turbulent region without accounting for the viscous sublayer. Okay. That is the simplest approach. That is what we are doing. Now, if you consider a fully turbulent region as the only layer, okay. So, then we actually can write this like this, correct. So, now you substitute mu t from the mixing length model. So, you have essentially Lm square, and what is Lm square? Von Karman constant square times y square, because in the fully turbulent region you do not have the damping function. So, that can be written as k square y square into, you have also du, so you have du bar by dy by nu into du plus by dy plus is equal to 1. So, can you now simplify this further? we can also write this as du plus by dy plus, correct. So, what do you get if you write it? So, I want to write this as du plus by dy plus the whole square. So, what will be the additional factor? This mu should be absorbed. Okay. So, just check that. So, finally, therefore, when we take square root of this and then we integrate it, so what will be the profile? So, we will have du plus is equal to dy plus by y into k. So, we will have du plus is equal to dy plus by, we can write this as y plus 1 by k. So, if you integrate this, this gets u plus is equal to 1 by k ln of y plus plus another constant. So, this is called the log law. Okay. So, this is the linear law. That means, if you assume only within the viscous sublayer, you have a linear variation of velocity with y. Now, if you assume only a fully turbulent region, you have a logarithmic variation of u with respect to y. Okay. So, the entire boundary layer can now be decomposed into profiles. In the viscous sublayer, you have a linear variation, and in the fully turbulent, you have a logarithmic variation. Okay. So, we will look at this, we will draw these profiles and try to now next move on to heat transfer problem, where we can use some analogies like the Reynolds analogy and calculate the expressions for Nusselt number. Okay.